discuss the mercury in a glass thermometer, no so?
Yes.
What do you say about mercury in a glass thermometer?
Mercury. Yes.
Can you give us some of the advantages of mercury glass thermometer?
Advantages.
Yes, so using mercury over water in a mercury glass thermometer.
It is okay. It expands uniformly.
It expands uniformly. Good. Thank you. Thank you so much. Let me hear from Benjamin. Benjamin.
It's easy to use.
It is easy to use.
Yeah.
Okay. Let me hear from members. Raise up your hand. I see you. Do you have anything to tell us about the last lesson? Okay. So in the last lesson, we saw mercury in a glass thermometer. We said that mercury in a glass thermometer, we use mercury because mercury, first of all, is opaque. I haven't started sharing my screen. I'm sharing it soon. We're still reviewing the previous lesson. So mercury in a glass thermometer, we said mercury in a glass thermometer is very important in the sense that for it is opaque, it expands uniformly, and mercury is also a good conductor of heat. Likewise, we said that water is not used in a liquid glass thermometer because it is transparent, it does not expand uniformly, and it's also not a good conductor of heat. So that's what we saw in the previous lesson. Today, we are going to build on from where we stopped in the previous lesson. We are going to see platinum resistant thermometer. Hope you can see my screen now. Good. Gift, can you see on my screen? Gift, unmute. Bob, can you see on my screen? Yeah, somebody says yes. Okay.
Yes,
good.
I can see your screen.
Okay, please, fine. So today, we are going to discuss platinum resistance thermometer. In the previous lesson, I had also given you a clue on platinum resistance thermometer. We said that we could have not used only platinum, but because of some conditions, we are forced to use platinum. And who can tell us some of those conditions? Some of those conditions which forced us see any hands up. Okay, Benjamin. Yes, Benjamin. Benjamin, let me see who is this. Who is this with the hands up? There's only one hand up. Benjamin, you unmute. I'm asking you to unmute yourself. Unmute and you tell us what you saw. Can you unmute?
Okay. It was somehow disturbing me.
Okay.
Platinum is used because it has a high temperature coefficient of resistance.
Very good. It is used because it has high temperature coefficient of resistance. That was good. Thank you. Thank you so much. So we use platinum because it has high temperature coefficient of resistance. That's why it is used as a platinum resistance thermometer. Is there another one? There are two conditions, of course. Is there another one? Yes, I see some hands up. Tendo. Tendo, can you unmute? Actually, there are very many hands up. I'm asking you to unmute. Please unmute. Tendo. Tendo, your network is not clear. I can't hear you. Tendo. Hello, Tendo.
The variation of resistance with temperature, platinum's variation of resistance with temperature is linear.
Very good, very good, very good. So we said there are only two conditions which must be fulfilled for a metal to be used as a resistance thermometer. One, it must have high temperature coefficient of resistance. Then two, it must vary linearly with the change in temperature. Its resistance must vary linearly with the change in temperature, of which I remember as we said platinum has all those two qualities. So if it has all those two qualities, we use it as platinum resistance thermometer. Good. We are saying a resistance thermometer uses resistance of a metal wire as a thermometric property, and these are the two qualities. The material of the wire should have high temperature coefficient of resistance so that for a small change in temperature, it causes a measurable change in resistance. That is one. Two, we said the variation of resistance with the temperature should be linear. And for that case, we said platinum is chosen to be used because it satisfies all the above two conditions. So that's why platinum is used. Now today, we're going to see the structure and mode of action. That's where we stopped. Structure and mode of action of platinum resistance thermometer. Platinum resistance thermometer is made up of a circuit. This circuit, I told you that this circuit is a circuit which we call to be a Wheatstone bridge circuit. This is a Wheatstone bridge circuit. A Wheatstone bridge circuit consists of or is made up of 4 resistors, which are arranged as you see in this rectangle, something like parallelogram. So that's our Wheatstone bridge circuit. And how does it work? I think I remember giving you briefly how it works. I want us to see very well, let us study very well the resistor R1 There's resistor R2. There is G in the middle. G in the middle is called, G which is in the middle is called moving coil galvanometer. That's the G in the middle. Then there is that rheostat S. The rheostat S is the adjustable resistor, this S. Then there's a platinum resistor, which is lowered into a silica tube. You can see this part. This is a platinum resistor. Now, briefly, how does a Wheatstone bridge work? It is what will give us how this resistance or the platinum resistance thermometer also works. A Wheatstone bridge circuit works on the principle that it works on the principle that when you adjust, let me pick a pen and I use it. It works on the principle that when you connect the circuit, this battery, when you connect it, current will flow. Of course, it flows from positive to negative. It will flow here. Then it reaches here by Kirchhoff's law in electricity. Some of you have already covered. It will divide itself into I1 and I2. So this I1 is going to go, it will flow here, then it will divide itself into I3 and I4. Then it also comes and then the thing continues that way. But with the help of this, when current flows through this one, through this galvanometer, we expect the galvanometer to deflect. But with the help of S, we can adjust this rheostat so that no current flows through the galvanometer. At a point where no current flows through the galvanometer, we say that the galvanometer gives no deflection, and at that point, we say the balance point has been reached. And what are the conditions of the balance point? For the balance point to be reached, this resistance is supposed to be equal to this resistance, and the resistance R4. You see, this is R4. And the resistance this side is supposed to be the same as the resistance that side for the balance point to be reached. So that is briefly the background of how it works. So, what do we do when it comes to platinum resistant thermometer? What you do, the platinum wire is put in ice. Okay? So the platinum wire, which is this, is put in ice. This is the platinum wire. It is put in ice. So a moment it is put in ice, automatically current is going to deflect through this. Current is going to flow through the galvanometer and it will deflect. So with the help of the rheostat, we shall adjust it until when it shows no deflection. At the point when it shows no deflection, we can calculate the resistance of the platinum wire using the balance condition. We said R1 over this equals to this over that. So we calculate the resistance R4. And that resistance becomes R0 because the platinum wire is in ice. Then from there, after determining R0, we again pick the platinum wire with the whole system. We put it in steam. When we put it in steam, we again adjust this one until when galvanometer shows no deflection. At that point where the galvanometer shows no deflection, we again determine the resistance R100. Then lastly, we pick it and then we put it in an enclosure whose temperature theta is required. We adjust this until when the galvanometer shows no deflection, we determine the resistance as R theta. So the value of theta, of course, you know, now this is Celsius scale because we have determined zero, temperature of 0 and also at 100. So theta from Celsius case will be the same as R theta minus R naught over R 100 minus R naught times 100 degrees Celsius. There you'll be in position to determine the value of theta. So let's see the procedures together. We're saying the platinum wire is put in ice and the variable resistor S is varied until the galvanometer. The galvanometer is the other small device I showed you in the middle, until it shows no reading. Some books they say until it shows no deflection. So that means that when you put it there, it will run. The current will flow through the galvanometer. So after you adjust the rheostat until the galvanometer shows no deflection. At this point, which point? At the point when the galvanometer is showing no deflection, I told you the balance condition. R1 is supposed to be equal to what? R2. And the resistance of the wire is equal to the resistance Rs. Let me get back to the diagram. At the point when the galvanometer shows no deflection, the resistance of this one is equal to the resistance of that. And the resistance of this one must be the same as the resistance of Rs. We make sure that this R1 and R2 are the same. So the resistance of this one is equal to the resistance of that. So you take the reading here directly. The resistance of S, which is the variable resistor, we call it Rs, of which it turns to be R naught on condition that this one is in ice. Then when this one is in steam, we adjust until when the galvanometer shows no deflection. When the galvanometer shows no deflection, the resistance Rs at that point is taken to be R100 because it will be also the same as the resistance at this point, which is in steam. Good. So you say that at this point, if R1 equals to R2, then the resistance of the wire is equal to the resistance Rs of the steam. And it's read and recorded as R naught. Why R naught? Because the wire is placed at ice point. Then from there, the platinum resistance is now, the platinum wire is now put in steam. And after being put in steam, the variable resistor S is varied until the galvanometer shows no deflection again. Then the resistance of the wire is equal to the resistance of S and is taken to be R100. Now we have taken at R naught, we have taken at R100, so we're going to take it at a temperature whose resistance is known. So now we say the platinum wire is now put in contact with a body of unknown temperature, theta. After putting it there, you vary the resistor, the variable resistor, until when the galvanometer again shows no deflection. At balance, or at that point, the resistance of the variable resistor S will be the same as the resistance of the platinum wire, of which it is recorded as R theta. So knowing R theta, knowing R naught, knowing R100, we can calculate the value of theta. The value of theta is then calculated from theta equals to R theta minus R naught over R100 minus R naught times 100 degrees Celsius. You'll be in position to determine the temperature of that. And that is how it works. If you have any question, you can raise up your hand, and then I repeat it for you. If you have all understood, you can still raise up the hand. You tell me that is well understood. So either ways, you have to raise your hand. Somebody confirm to me that there's no question. Bob?
Yeah, sir, it is okay.
It's okay, good. Thank you. Let me hear from Collins. Collins? Atwine? Robert, your hand is up. Robert?
So there's a step behind which I never understood. So
I can repeat it.
the
Which step?
platinum wire is, which says the platinum wire is now put in contact with a body of unknown temperature theta.
Yes.
And with the variable resistor. And the variable resistor is valid until the galvanometer shows 0.
Yes.
There, that step there.
So you're saying, okay, Bob, are you there?
Yeah, I'm
Bob?
there, sir.
Good. So you're saying that we first put it at ice point, okay?
Yes.
We put it in ice, then we determine the resistance R naught. Is that okay?
Yes, sir.
Then from there, we put it in steam. When you put it in steam, still you will adjust the variable resistor until when the galvanometer shows no deflection. You determine R 100, okay? Remember, what we are looking for is looking for how does it work? How can it be used to measure the temperature of a body? Is that okay?
Yes.
So now we transfer it and we put it in an enclosure or in contact with a body whose temperature is now required. Okay?
Okay.
Then from there, you determine the resistance, R theta. How do you determine R theta? You vary the variable resistor until when the galvanometer shows no deflection. Then from there, you read R theta direct. Is that okay?
Yeah.
Good. Robert says, got you, sir. Okay, thank you. Good. I'm not seeing more, any other hands up. That means that you're giving me a go ahead. Can I go to the next thing? Good. The next thing is here. Advantages of platinum resistance thermometer. That is our next thing. Let me first remove it and then we brainstorm ourselves. What do you think are the advantages of platinum resistance thermometer? By show of hands, what are the advantages of platinum resistance thermometer? I see hands up. Yes, Collins, Atwine, and Rina. Let me hear from Rina first. Rina?
Yes, sir. I think it has a very high degree of accuracy due to platinum varying linearly with temperature.
I like your submission for sure. And even the reason which you have given, okay? It is
Yes, sir.
very accurate due to the fact that platinum satisfies all the other two conditions. Platinum has very high temperature coefficient of resistance. Platinum resistance varies linearly with change in temperature. For the two reasons, we say that it's very accurate. Thank you so much, Rina. Let me hear from Collins.
It is very sensitive to small unit temperatures.
It is very sensitive to a small unit temperature. The fact that it's very linear and also has very high temperature coefficient of resistance makes it very sensitive. Thank you so much for that wonderful submission. But I see some hands up. Tekuno, are you Tekuno? What is your name?
I'm Precious.
Precious, I'm going to rename you. Precious who?
Precious Akankunda.
Okay, Precious, I've renamed you already. Good. Yes, Precious, you can go ahead.
It is easier to use than that of a gas thermometer.
It is easier to use, okay?
Than that of gas thermometer.
Than that of the gas thermometers. Good. So those are some of the advantages. Let's list them down. You're saying it is used, you can measure its used to measure very small unit temperature. Somebody gave it to us. 2, it is very accurate. Actually, this point was put clear by one of us, that's Rina. It is very accurate because the resistance of platinum wire varies linearly with the temperature. Somebody forgot to give me this. You can measure from negative 200 degrees Celsius to 1,200 degrees Celsius. Is it big? Yes. Isn't that one very big?
Yeah.
It's very big. Unlike liquid glass thermometer, which measures up to 100 degrees Celsius. Good. I see one hand up. I'm trying to look for you. Who is this one with the hands up? Please go and chat with me. Precious, are you the one?
I'm not the one.
Somebody's having hands up. I'm not seeing him. Okay. So we're saying it has wide range of temperature, that is from negative 200 to 1,200 degrees Celsius. And then is very sensitive to very small change in temperature. Good. Could you be knowing some of the disadvantages of platinum resistant thermometer? If you know, you can raise up the hand. Yes, Tendo. Tendo.
It's bulky.
It is bulky. You cannot steal it. You can't put it in the pocket. You know, some of us used to be thieves in high schools, eh? So we would want to steal everything in a laboratory, and each time we are going to steal, we would say it is our school money, our money, our money. So we just want to. Even one day, somebody wanted to steal a test tube. Now you steal a test tube, you use it for what? Okay. Let me hear from John.
It cannot measure very rapidly changing temperature because it has low thermometric conductivity and high heat capacity.
Very, very good. It can't be used to measure rapidly changing temperature because of its low thermoconductivity. Thank you so much. Farazi? Usna Farazi?
Due to the size of the tube, this thermometer cannot be used to measure temperature at a point.
It can't be used to measure the temperature at a junction or at a point. Thank you. Thank you so much, you guys, for the wonderful submission. They are really impressive. Joe Lovins.
Sir, can I say it is also very expensive?
Yeah, it is also, it is okay. Because now when you compare with the liquid in a glass thermometer, they cannot be of the same prices. So you can say it is, now it depends on what you're comparing it with, okay? When you compare with liquid in glass, thermometer is more expensive than the other. Good. Let's see the disadvantages. One, it cannot measure very rapidly changing temperature. Why? This is because it has low thermal conductivity and high capacity. We shall not discuss thermal conductivity here, but it is under heat still under this, and it's also not discuss heat capacity. We shall discuss it after. But heat capacity is just a quantity of heat which is required to raise the temperature of a substance by 1 Kelvin. Then when we talk of thermal conductivity, the fractional change in temperature of a body. We're saying, two, it cannot measure temperature at a point because of its size, the size of the silica tube. You cannot measure temperature at the point. A temperature at the corner, a temperature which has been of a body which is hidden. Then three, it is heavy, and for that case, it is not portable. So this one you can use the other one, which Robert gave us. It is bulky. You can't steal it. It is bulky. You cannot put it in the pocket, and it's very heavy. So those are the three main. Much as others may come, but those are in comparison with others. But these are the three main disadvantages of platinum resistance thermometer. Good. Any questions so far? I see Precious has raised up the hand. Precious, you can say what you want to say. Yes, Precious, the floor is yours.
I'm saying, boom. Is it not possible? Is the same as bulky?
Not portable.
Hello. Not portable is the same as bulky.
Yes, not portable. You can use the word bulky. It is bulky. Is that okay?
Yes.
Good. I see some hands up. Rina.
Excuse me, sir. Is it right to say that it doesn't give direct readings?
Does not give direct readings. Yeah, the truth is, when you see most of the thermometers, did you see a liquid in a glass thermometer? It was also R theta equals to R naught minus R. It was R theta, L theta minus L naught over L theta, L 100 minus L naught times 100, okay? So it's a commodity to all the types of thermometers we are going to see. So it may not be taken as the disadvantage, though it's true. Tracy says, teacher, what if I say it is slow, but no reason? It's okay, Tracy. It is slow, as in the person you say that you don't have any reason for that. But it is yes, the fact that we said it does not measure rapidly. You see this statement does not measure rapidly changing temperature. That means that it is slow in response. If the temperature changes very fast, it is unable to measure it. It needs a temperature which is moving uniformly and slowly. What is the level of accuracy? It is very accurate. I cannot give the percentage, but it depends on the operator also as well. but it's very accurate. The reading, if you see the advantage, it's very, very accurate because the resistance of platinum wire varies linearly with the temperature. Didan says, can I say that it does not measure very high temperatures? We have given this as an advantage already. Said it can measure a wide range of temperature. So if we have said that it measures a very wide range of temperature, 1,200, you people have to believe me that it is some good temperature. With a temperature of 1,200 degrees Celsius plus, can you agree with me that that temperature is very high? It is very high, really. No, sir. Yeah, really, that temperature is very high. We can say that you cannot make very high temperature. Okay, good. Thank you. Then Mr. Bernard says, where are learners today? Mr. Bernard, we are in physics class. We are not very many. We are always, actually today we are very many. This used to be 10, 15. And today we have 18. Good. So these are the disadvantages of platinum resistance thermometer. I go to calculations. Is that okay, everyone? Is it okay?
Yes.
Good. Calculation number 1. Precious, can you read for us that question? Precious, can you read for us that question? If you cannot read, let me call upon Collins. Collins, can you read for us that?
The resistance of a particular resistance thermometer at Celsius temperature theta as measured by a constant volume gas thermometer is R theta is equal to 50 plus 0.17 theta plus 3 times 10 to the power negative 4 theta squared. Calculate the temperature as measured on a scale of resistance thermometer, which corresponds to a temperature of 60 degrees Celsius at a gas thermometer.
Thank you so much. Thank you, thank you. Good. Let's see how we can go about with that. We are saying the resistance of a particular resistance thermometer at set temperature theta as measured by a constant volume gas thermometer is this. Calculate the temperature as measured on a scale of the thermometer that corresponds to a temperature of 60 degrees. Please, I want us to be careful here. The resistance at any temperature is given by this expression. Do you get this? The resistance at any temperature is given by this expression. So we are asking, what is the temperature at 60 degrees? Before I get the temperature at 60 degrees, I need the resistance at what? At 60 degrees. Is that okay? Is that fine, everyone? Good. I need the resistance at 60 degrees. I need the resistance at 0 degrees. I need the resistance at 100 degrees. Is that okay?
Yeah.
Then we use theta equals to what? R theta, no so? Minus R what? R naught over R what? R 100. Is that okay?
Yes.
Minus R what? R naught, then times 100 what? 100 degrees Celsius. Is that okay? Of which this R theta is the resistance at 60 what? 60 degrees. Is that fine?
Yes.
Good. Let's start it together now. Let's start it together now. So, we start as a solution. We have our R theta at any temperature is given by that, okay? Please be with the calculator. So we are going to start with theta equals to 0 degrees Celsius. So when theta equals to 0 degrees Celsius, that means that where there is theta here, we substitute what? 0. Is that okay? So we shall have R naught. That will be R naught equals to 50 plus 0.17. Instead of theta, we shall put what? 0. Is that okay, everyone?
Yes.
Then here we also put what? 0. Is that okay? So all of this one is 0. This one is also 0. So our R naught will be equal to just 50 ohm. Did you get that? Did you get that?
Yeah.
Can somebody get for me R100, please? Who's going to get for us R100? Raise up the hand. Who's getting for us R100? Yes, Robert. And Benjamin. Robert and Benjamin get for us R100. I'm giving you two seconds. I mean, 20 seconds.
Okay.
Right.
67.3.
Benjamin, what do you have?
I'm getting 67.
67.3. So let's check together. So we have R100 at 100. We shall have R100 to be equals to 50 plus 0.1 into 100.
Ohm. It's an ohm.
Yes.
Yeah.
So when theta we put just 100 here, then we also put 100, but square, don't forget to square it. So 100 and 100 square. You forgot the square?
Yeah.
Let's change it. So R100 would be 70 ohms. Yes, Robert, you can talk.
So it was 100.
Yes, 100 ohms. Hello, was it 100 ohms?
No, it is 70.
It is 70, eh?
Yeah.
Okay. So that is R 100. Is that okay? Remember, they want the temperature at 60 degrees. So if they want the temperature at 60 degrees, pressure says minus 67. Technospark says minus 70. and then it is 70. Now let's go to 60 degrees. At 60 degrees, can we calculate 60 degrees? What do you get? Please confirm to me. I want to hear your answer. 60 degrees, what do you get?
61.8. $6.4.
You have got what? Let me see on the chart. 61.28, 61.28. Bob Muller. Let's confirm. Is that ALIRA equals to 61.28. Then from there, we say from ALIRA theta, from theta equals to ALIRA theta minus R naught over R 100 minus R naught times 100. We substitute. Please, can you substitute and you get for us the answer? Somebody's raising up the hand. Yes, John. John?
56.4 degrees Celsius.
56.4 degrees Celsius. Yes, Osbert. Robert, I mean. $56.4 from Tracy. Rina says 56.4. Good. So let's go there and check whether it's that. Let's see. So it is 56.4 degrees Celsius. Is that okay? Is that fine, class? Yes, Matthias, I see your hands up. Matthias? Matthias, I see your hands up. You have taken it down. So class, can we go to the next? Yeah. Benjamin says, yes, teacher, it is okay. Atune Collins says, yes, teacher, it's very fine. So let's go to the next number. Let's go to the next number. Can for us that question?
The resistance of the wire as measured by a gas thermometer varies with temperature according to the equation. R theta is equal to R naught into 1 plus 50 alpha theta plus 200 alpha theta squared. Determine the temperature on the resistance thermometer that corresponds to 40 degrees Celsius on the gas scale.
Thank you so much for that. So this is almost the same as the other one. The resistance at any point is given by, at any temperature is given by R theta equals to R naught into 1 plus 50 alpha theta plus 200 alpha theta squared. Determine the temperature of resistance thermometer that corresponds to 40 degrees Celsius on the gas scale. So, if that's the case, then we rate this. After we also get at 0 degrees. After getting at 0 degrees, we get at 100 degrees. Then after we get the resistance at 40 degrees. Is that clear? Okay, fine. Benjamin, I see your hands up.
Denzo, don't bring here play. You can play from outside.
Benjamin, you can unmute and say something.
Teacher, I wanted to ask, what about the alpha?
What about the alpha? We shouldn't worry about alpha. For us, we do what we think is correct. The rest we sort out itself, okay?
Denzo, you get out and you play from out. I just go to this.
Okay, Benjamin. Yeah, good. So, okay. So let us start. At 0 degrees, when theta equals to 0 degrees, what will be R naught? Who can get for us that answer? Who has got for us R naught at when theta is 0 degrees? Yes, Benjamin. What have you got?
I think it's R naught.
Good. Let me hear from Rina. Rina, what have you got? Rina? Okay. So let's substitute. We substitute from R theta equals to R naught into 1 plus 50 alpha theta. So where there is theta, when theta is 0, we put 0 here. So the whole of this one will be 0. And even this part will be 0. So we shall have R naught equals to R naught into 1. So R naught equals to R what? R naught. That is 1. Then we go to theta equals 100 degrees Celsius. When theta is 100 degrees Celsius, we substitute. We shall have R100. We shall have R100. Please somebody give me the calculator. Will be equals to R naught. R naught 2, 1 plus. This will be 100 times 50. What is 150? What is 100 times 50?
5,000.
5,000.
So it will be 5,000. But what? The alpha, do you see alpha is there?
Yes.
Then plus. Then here we are putting 100. So it will be 100 squared times 200. What do you get?
2 million.
2 million.
2 million.
2 millions.
Yes.
Good. But 2 million what? Alpha. Did you get that?
Yes.
2 million alpha. So that means this one can be added on this, no so?
Yes.
So what is R100 when you add them up? Let's hurry up, our time is up. This R naught into 1 plus what? This is 2,005,000. Isn't it 2,005,000?
Yes. We add the one.
No, one cannot be added because we are adding those one with alpha only, the alpha only.
Okay.
Yeah. 2,005,000.
Yes.
Alpha. Is that okay?
Yes.
So this is our R 100. Good. So our R 100 will be R naught into 1 plus 2,005,000 alpha. Is that okay?
Yes.
Good. Now we go to when theta is 40. When theta is 40, that means that we shall substitute here 40 and also 40 here. Is that okay? We shall have R 40. Yes, Benjamin, I see your hands up.
That's the answer that I had.
Okay.
Yeah.
So from there, what we do, we substitute in the expression from theta equals to R theta minus R naught over R 100 minus R naught times 100 degrees. Our R theta is R 40. So R theta is R 40. So you bring and put it here, which is R naught plus this minus R naught over R 100 was this minus R naught times 100. Then if you realize this one, they are common. Do you see that? R naught common, R naught common. Is that okay? Is it fine?
Yeah.
So we pull out R naught from up. When you pull out R naught, here we shall remain with 1 plus 32,000, I mean 322,000, and then alpha minus 1. Because R naught is already common, you pull it out. So we shall have this one, then minus 1 here. Over, here we also pull out R naught. So we shall have the whole of this one minus 1 there. And then this one and this one will go. Is that okay? Do you see that? Are we able to see that one?
We don't want it.
Then this one and this one will also go. Is that okay? Then R naught and R naught will also go. Is that fine?
Yes, sir.
So eventually we shall remain with only this.
Mine, we are going to dart it again.
So when you reach this one, alpha and alpha will go. Is that okay?
Okay, don't dart it. Don't dart it.
Good. Okay, we are ending. So when you divide this by this, what do you get? Times 100, do you get 16.06? Please confirm, and then we end the lesson.
Yes, it's 16.06.
Good, good. Is there any question? If there's no question, please, I thank you very much for attending. I'll put the work on Google Classroom. Make sure you're there, and also on our WhatsApp group. Let me call upon my co-host, who is also my boss, to say a word to you before you go. Yes, Mr. Bernard. Yes, Bernard. Hello, Bernard. Thank you, class, for attending. How can I join the WhatsApp group? You can, I'm posting my number there. You can text me on that number. I will text you there. Just text me on that number.
I'm not seeing it.
The number is 070. Okay?
Yes. Yes.
070 375
Yes.
0387.
87.
0387.
Yes.
Can I repeat for you?
We have got it.
It's 07037500387. Is that okay?
Yes, sir.
Kale, thank you. See you in the lesson, next lesson. Thanks so much for attending. Goodbye for now.
Okay.
Okay, please. See you.
Oh, wait.
Goodbye. You can leave the class.